Hello students, welcome back to 60 out of 60 in KCET Chemistry 2025 series in just 200 days. So we have now completed the PU2 chapters and we have already started the PU1, and today we will be completing the second chapter of PU1, that is structure of atom. So in this video I will be discussing about the quantum mechanical model, okay, in detail. What were the, how it came into existence, what are its postulates and all, we will be seeing, okay. So as I say in my every video, please join our WhatsApp channel, link is there in the description section, and this will help you to get PDF notes and get access to our mock test and solutions, okay. So now coming to the structure of atom, as I told you, we'll be covering it in three parts. So in the first part we have already done with the discovery of subatomic particles, atomic models, and in part 2 we have already discussed developments leading to Bose model and Bose model, and next in today's lecture we are going to discuss towards quantum model and quantum mechanical model, okay. So now year wise weightage, so every year one question you can expect from this particular chapter, okay. So now in this one, towards quantum mechanical model, okay. So what do you mean by this word towards quantum model? Means, as you see in the Bohr's model, there were some developments before Bohr gave his model, right, and he took conclusions from these models and then he proposed his atomic model, right. Similarly, before quantum model also there were some developments, okay, some scientific researches were going on which gave some very important conclusions, and based on these conclusions the quantum mechanical model of the atom was designed, okay. So now if you see what is what were these observations or these developments that led to the quantum mechanical model, so that thing we'll be discussing. The first thing, dual behavior, the first thing here is the dual behavior of matter, okay, and the second thing is Heisenberg uncertainty principle, okay. Now these were the two developments which led to the quantum mechanical model, and after that we'll be talking what is this quantum model, and in this we have so many things to discuss, that is its postulates, what is node, quantum numbers, energy, rules, and then electronic configuration, okay. And with this we'll be completing this chapter today. So first let us start with towards quantum mechanical model. So the first thing is the dual nature of matter. So now as we see that electromagnetic radiations have wave-like properties was known to us, but with black body radiation and photoelectric effect we came to know about the particle nature of electromagnetic radiations, right. Now similarly the scientists say that if radiations can have two forms, that is particle nature and wave nature, then the matter or the particles or the matter can also have two natures, that is wave and particle. Are you getting? See here, so what I am saying is radiations, okay, radiations were earlier believed to have wave nature, okay, but later with what, with black body radiations and photoelectric effect, okay, with these two we came to know that even radiations can have particle nature, right. Now in contrast to this, if you see analogy, if radiations can have both wave and particle nature, then matter can also have both wave and particle nature, okay. So that was told by a scientist, that is de Broglie, and he proposed that matter also possesses both wave and particle nature like radiations, okay. So now if you see, matter was, radiations was believed to have wave nature, we all knew that. Similarly matter was believed to have particle nature, okay. Here we need not have we do not have to prove anything. Similarly for radiations to have wave nature we need not prove anything, okay, but similarly matter having particle nature was very obvious. But if matter is also having wave nature, right, if it is having wave nature then it will have wavelength also, right. So to calculate that wavelength, okay, so de Broglie gave a formula. What is this wavelength? This is the wavelength of matter, okay. So what is this formula to calculate? H by P, okay, or I can say H by mv. P is here what? H is your Planck's constant, that is 6.63 into 10 to the power of minus 34 joule seconds, and P is momentum okay, momentum which is equal to mass into velocity. Okay, that is what is given here. Clear? I hope this part is clear. De Broglie. So this dual nature of matter was given by de Broglie. That is the first development towards quantum mechanical model. Next, coming to Heisenberg uncertainty principle, the second one, okay, the second development towards quantum mechanical model. Now Heisenberg was another scientist who said that it is impossible to determine simultaneously the exact position and the exact momentum of an electron. Okay, so according to Heisenberg, it is not possible to determine the exact position and momentum of an electron. Okay, momentum, when we talk about velocity. Okay, of an electron, we cannot find it out simultaneously. Now how can we explain this? So here you can understand, suppose we have a, like for example, we have a nucleus here and we have an electron here. You want to determine the position of this electron. Okay, then you need to put some, suppose you want to see this electron, just imagine you want to see this electron. To see this electron, you need to put some light. Okay, or when you put the light, okay, these electrons size is very small, right? That means the light you are using, okay, the light you are using to see this, its wavelength should be less than the size of electron, or should be equal to the size of the electron. Okay, now if the wavelength is very small, okay, if the wavelength is very small, then what will happen to its energy? Energy will be very high, right? Now we know that radiations are small packets of energy, right? Now what happens when this radiations which can detect this electron is put on the electron, this radiation which is having very high energy transfers its energy to the electron. Okay, now if it transfers the electron, the energy of the electron will increase, then definitely the momentum will change, right? The momentum will change. So that is why it is said that you cannot determine both the position and the momentum of the electron simultaneously. If you cannot understand this one, once again listen. Suppose this is an electron, okay, very small particle, and I want to observe it. So what will I do? I'll put some light on it. So suppose this is my torch, I'm putting the light on this electron. Now what happens? To observe anything, the size, the radiation that you are putting here, its wavelength should be comparable to the size of the electron. Now electron size is very small, that means the wavelength will be also very small. If the wavelength is very small, then energy will be very high. So when you are putting this light on this particle, you are putting a very high frequency, or I can say high energy radiation. So when this radiation hits the electron, it will be visible, but when the radiation is hitting the electron, at that time it is transforming some energy to the electron. Now once electron absorbs this energy, okay, its momentum will change. So no doubt you located the electron correctly, or you were able to calculate the position of the electron, but at that time the momentum of the electron has already changed. So that is why we cannot calculate the momentum and the position of the electron simultaneously. Okay, so that is what is your Heisenberg uncertainty principle. Now what was the formula for this? The formula for is delta x into delta px is greater than or equal to h by 4 pi. So what is here delta x? Delta x is uncertainty. So I'll write on this side. Okay, one second. So this I hope is clear, this explanation. Okay, so now what is delta x here? Delta x is uncertainty. Okay, uncertainty in position. Okay, next we have delta px. Delta px is uncertainty in momentum. Okay, and h you know already, Planck's constant, and pi is 3.14. Okay, next, what is the significance of this Heisenberg uncertainty principle? So Heisenberg uncertainty principle ruled out, or you can say it was the reason why Bohr's model failed. So now according to Bohr's model, what was the postulate here? That electrons travel around, or electrons revolve around the nucleus in fixed orbits. right? So that means electrons position and the energy of these orbitals were fixed. That means energy of the electron has already been calculated. If energy is calculated, we can calculate momentum also, and because it is rotating in fixed, it is revolving around the nucleus in fixed path, its position is also known, right? So according to Bohr's model, both the position and the momentum of the electron could be calculated easily, okay, simultaneously. But according to Heisenberg principle, that is not possible. So in that case, the Bohr's model was ruled out. So the significance is that it rules out the existence of definite path or trajectories of electrons and other similar particles, okay. So that is what Bohr said, that electrons travel in fixed path around the nucleus. But now with the Heisenberg principle, that we cannot measure the location or the position and the momentum of electrons simultaneously, this concept that electrons travel in fixed path was cancelled, okay. So now coming to what is then the conclusion that we can draw from here. What can be the conclusion here? So you can see here that it means that the precise statements of the position and the momentum of electrons have to be replaced by the statement of probability. Now we cannot say that according to Bohr's model, we can say you were able to calculate the radius of the orbit, right, where the radius will be present, where the electron will be present. So but now we cannot say that the electron is present there, but we can say that probably the electron is present there. We think that the electron may be present in this case, but it can be present, it cannot be present also, okay. So the statement of precise statements, exactly you can say this is present here, has now turned to probability, that the electron has at a given position and a momentum. So we can say that suppose you are calculating the radius of the orbit and you are telling that electron is present here. So you can say that probably the electron is present here. You cannot say that the electron is present here because you cannot measure the position accurately, okay. So this is what happens in the quantum mechanical model of the atom. So when we'll talk about that, we'll discuss, okay. Now coming to the reasons why Bohr's failed. So there are two important reasons. The first reason is the wave character of the electron is not considered in the Bohr's model. So in the Bohr's model, electron was considered as a particle, okay. And the second thing is obviously an orbit is a clearly defined path, and this path can completely be defined only if both the position and the velocity of the electron are exactly known, okay. So according to Bohr, electrons traveled in a definite path, and we can explain this definite path if we know the velocity and the position of the electron at every point of time, right. But according to Heisenberg, that is not possible to calculate. So that means electrons do not have a definite path, okay. So here is the reason why the Bohr's model failed. Now we will go towards the quantum mechanical model. So when Bohr's model failed, the new model came, that is the quantum mechanical model of the atom. So according to quantum mechanical model, the wave nature of the electron was considered, okay. And they considered that these electrons are wave nature, okay, and these electrons are having some wave-like properties, and each wave is the solutions. I'll be explaining that, but let us see here. See, when Schrödinger equation is solved for hydrogen atom, the solution gives the possible energy levels the electron can occupy and the corresponding wave function of the electron associated with each energy level, okay. So now what happens, that there was a scientist Schrödinger, okay. He gave an equation called as Schrödinger equation, okay. Now when you solve this Schrödinger equation, the solutions that were obtained for this Schrödinger equation was helpful to determine the position of the electron, okay. So now you see, when Schrödinger equation is solved for hydrogen atom, the solution of this equation, okay, gives the possible energy levels. Here you can also write, you can see the word possible, means it talks about the probability. The solution gives the possible energy level of the electrons can occupy and the corresponding wave function of the electron associated with each energy level, okay. So now based on these solutions, we'll get different energy level and the wave function associated with it. Now these quantized energy states and corresponding wave functions are characterized by a set of quantum numbers. Okay, so the solutions of these Schrodinger equations, okay, solutions gave you position of the electron, and these solutions were called as quantum number. Okay, these quantum numbers are principal quantum number, azimuthal quantum number, and magnetic quantum number. Okay, now we'll see this so now this is what I'll tell you in summary. Schrodinger was a scientist. He gave a equation, Schrodinger equation, and when you solve this equation, the solution of this equation will give you the position of the electron. Okay, so next, when an electron in any energy state, the wave function corresponding to that energy state contain all the information about that electron. So we have, like, see, this is, we have different energy levels. Okay, different energy level, and each energy level is associated with a wave function psi. Okay, this is called as wave function psi. Now when you solve this wave function, or when you get the solution of this Schrodinger equation, you can tell the position of the electron. Now such wave functions of hydrogen or hydrogen like species with one electron are called as atomic orbitals. Okay, next, the such wave functions pertaining to one electron species are called as one electron system. Okay, so this is not important. Next, the probability of finding an electron at a point within an atom is proportional to psi square at that point. Okay, so what is the probability of finding? So see, this is energy levels. Okay, so electrons will be found on these energy levels. Okay, and these energy levels are dedicated, are called as atomic orbitals, or by a you can say, or by a wave function. Okay, now the probability of finding the electron anywhere in the atom is proportional to psi square. Okay, so now we will discuss about the quantum numbers. So what are the quantum numbers? Quantum numbers were the solutions of Schrodinger equation, right? And these quantum numbers helps you to find the position of the electron. So there are 4 quantum numbers. So we have discussed there are 4 quantum numbers. The first quantum number is principal quantum number. Okay, the second quantum number is azimuthal quantum number, and the third quantum number is magnetic quantum number. Okay, now see, principal quantum number, okay, tells you the shell in which the electron is present. We'll discuss all this. So first let us understand, it tells you about the shell in which the electron is present. Azimuthal quantum number tells you the subshell in which the electron is present. Okay, then magnetic quantum number tells you the orbital in which the electron is present. Okay, first thing over. Now second thing is, the principal quantum number tells you about the size of the shell in which the electron is present, or orbital in which the electron is present. Azimuthal quantum number tells you about the shape of the orbitals, and magnetic quantum number tells you about the orientation of the orbitals. Okay, now third one, with principal quantum number you can calculate the energy of the electrons, and with azimuthal quantum number you can calculate the angular momentum of the electrons. Angular momentum. Okay, now fourth one, coming to range. Okay, so the principal quantum number starts from n is equal to 1, 2, 3, okay, 4, like this. Okay, next we have azimuthal quantum number. So one more thing, principal quantum number is denoted by n, azimuthal quantum number is denoted by L, and magnetic quantum number is denoted by ML. Okay, now what is the value of azimuthal quantum number? It is from 0 to n minus 1. 0 to n minus 1. I'll be giving you example and it will be very clear. And next, what is the range of magnetic quantum number? It is minus L to plus L. Okay, so now let us take one example and understand. Okay, suppose we have, so here I am writing like this. Yeah, so suppose I have n is equal to 1. Okay, if n is equal to 1, then that means principal quantum number is n. Then what is the value of its azimuthal quantum number, or L? So you can see L starts from 0 to n minus 1. Okay, so n is here 1, so 0 to 0. That means I can say that the L value here is 0. Okay, One second, I'll write like this. We have here N, L and ML. Okay, so now for N is equal to 1, L value is 0. Okay, and if you see, ML values will be what? Minus L to plus L, right? Minus L to plus L, that means minus 0 to plus 0, and that does not exist, so that is also here 0. Okay, so sorry, 1 minute. So we have here, so ML will be, so magnetic quantum number will also be equal to 0 here, right? Now if I take N is equal to 2, now if you see N is equal to 2, okay, now what is the value of L here? L value will be 0, 2, 2 minus 1 is 1, so 0 and 1, so we have 0 and we have 1. So for ML here it will be 0, because for L value 0, ML value will be 0, but here I will have what? For L value equal to 1, the ML value will be minus 1 to plus 1, right? So that means minus 1, 0 and plus 1. Now if you see 3, so if N value is 3, okay, then what is the value of L here? L value will be 0, 1 and 2, right? So for L value 0, the ML value will definitely be 0. For L value 1, the ML value will be minus 1, 0 and plus 1. And for L value 2, the ML values will be minus 2, minus 1, 0, plus 1 and plus 2, right? Like this we can see. So now if you see here, for L values, okay, so there are some nomenclature here. If L value is 0, it is named as S. If L value is 1, it is P, and if L value is 2, it is D. Okay, it will go further also. So now I can write that this is S, so I can name it as 1S, okay, and here it is 2S, and here it is 2, and here it is 2P, okay, 1 second, okay, so here it is 2P, okay, then we have 3S for this one, then I have 3P, and I have here 3D, okay. So I can say that 2p subcell, okay, 2p has how many orbitals? 2p has 3 orbitals, 3s has 1 orbital, 3p has again 3 orbitals, and 3d has 5 orbitals. I hope you are getting it. Okay, next coming to nodes. Okay, node is something or the reason where the probability of finding the electrons is 0. Okay, so there are two types of nodes here, radial nodes. How to calculate radial nodes? The number of radial nodes is n minus L minus 1. Here n is principal quantum number, L is azimuthal quantum number, and okay. Next we have angular nodes, and angular nodes is L, that is your azimuthal quantum number. Okay, so once again we'll revise the quantum numbers here. Okay, I'll write it once again. So if you see, you have N, L, so I'm making it again so that if any one of you haven't understood till now, it will be clear once again. Okay, it's little complicated, but yes, not very difficult. So you have N, you have L, and you have ML. Okay, so first I will take N is equal to 1. If N is equal to 1, the L values varies from 0 to N minus 1. 0 to N minus 1, here N is 1, so 1 minus 1 is 0, that means it is 0 only. Okay, that means this is S. So this one can be called as 1S. Okay, so this 1S in ML value also it is 0 only. So in this 1S we have only, this is how we can represent 1S. Okay, with a box. Now if I come to N is equal to 2, okay, for N is equal to 2, we have, what are the L values? L values are 0 and 1. So we have 0 and 1. Okay, so for 0 it is 2S, and for 2S, and this is 2P, right? Now this is also 0, and this is minus 1, 0 and plus 1, right? So we can write this one as 2S, okay, and this one as 2P. So in 2p you see I am making 3 orbitals, right? In 2p there are 3 orbitals. One is minus 1, one is 0, and one is plus 1. Now if I come for 3, okay, for 3, what are the L values? I have 0, 1 and 2. So you have 0, 1 and 2. So that means it is 3s, 3p and 3d. Okay, now 3s value as what? 3s has only 0. P is having minus 1, 0 and plus 1, and D is what? Minus 2 to plus 2. So we have minus 2, minus 1, 0, plus 1 and plus 2, right? So it is 3s, we have like this 3s, then we have 3p, that is 3 we have, and then in 3d you are having 5 orbitals. Okay, so 1, 2, 3, 4, 5. That is how quantum number works. Okay, fine. So we also discuss about the nodes. Next is energy. So now we will see here how to calculate the energy of the orbitals. Okay, so to calculate the energy of the orbitals, we follow a rule. Okay, and that rule is called as your n plus L rule. Okay, so one second. Yeah, so that is your n plus L rule. Now what is this n plus L rule? So here n stands for your principal quantum number and L stands for azimuthal quantum number. So to calculate the energy of the orbitals, you need to add their n and L value. Whosever n plus L value is higher, their energy levels will be higher. Okay. Now for example, if you consider like 1s and 2s. Okay. So 1s n value is what? 1. L value is, because it is 0, it is because it is s, it will be 0. Here n value is 2 and L value is 0. Now if I add here, it is 1, okay, and if I add here, it is 2, right? Now if you see, the n plus L value of 2s is higher, right? That means 2s energy will be more than 1s. Okay, so that is 1s will have 2s will have more energy than 1s. Clear? Now similarly, if you check like for example 3d and 4s. Okay, so 3d, if you check what is the n value of 3d, n is 3 and n is 3 and you have L value SPD 0, 1, 2. Okay, so that is 2. So that is n plus L value is 5. Here n is equal to 4 and L value is 0. So that is n plus L value will be 4. Right. So now if you see whose n plus L value is higher here, 3d n plus L value is higher, right? So that is why the energy of 3d will be more than 4s. Now a question may arise, ma'am, what if the n plus L values comes to be same, right? So for example, if you take 3d and 4p, okay, so 3d, what is the n value? 3, L value 2. Here what is the n value? 4, L value 1, right? Now if I add this, this is also 5, this is also 5. In this case, how to differentiate or how to find out? In this type of cases, the one whose n value is greater, its energy will be greater. Now here n of 4, the 4p n value is greater, so that is why this one will be higher. Okay. So that is how you can calculate the energy of the orbitals, and once the energy of the orbitals have been calculated, this is the order. 1s, then we come 2s, then 2p, then 3s, okay, then we have 3p, then 4s, then you have 3d, 4p, 5s, then you have 4d, 5p and 6s, then it goes here to 4f, 5d, 6p, 7s, and after that we have 5f, 6d, 7p and 8s. Okay, so need not remember up to this, you can just remember up to like 3d, 4s. After that you can remember, that will be doing your work. Fine. Now let us feel that how to fill the electrons in the orbitals. Okay, there are 3 rules which you should obey while filling the electrons in the orbitals. Okay, the rule number 1 is Aubert principle, and Aubert principles tells you that the electrons in the ground state of the atom, the orbitals are filled in the order of their increasing energy. So just now we saw the increasing order of energy. So first 1s will be filled, then 2s will be filled, then 2p, then 3s, then 3p. According to the order of the orbitals, the energy should be filled. Okay. Next we have Pauli's exclusion principle. What does this Pauli's exclusion principle tells you? That no 2 electrons in an atom can have the same set of 4 quantum numbers. Here a question is arising, ma'am, you have told us only 3 quantum numbers, right? Principal, magnetic and principal quantum number, magnetic quantum number and azimuthal quantum number, right? Then what is this 4th quantum number? So the 4th quantum number here I'll introduce is your spin quantum number. Okay, and this spin quantum number has only 2 values, that is plus minus half. That means the electron can rotate clockwise or anti-clockwise. Based on that, it gets plus minus half value. Okay, so all these 4 quantum numbers of electrons should be unique. Okay, no 2 electrons can have the same values of all the 4 quantum numbers. Okay, it can, at least one should be different. Okay. Next we have Hund's rule of maximum multiplicity. This tells that electrons in the orbitals belonging to the same subshell, okay, does not take place until each orbital belonging to that subshell has got one electron each. It is singly occupied. Now let us understand this in detail. Suppose you want to fill the 3p orbital, okay, suppose you have 3p orbital, okay, and if you remember in 3p or any p you will be having -1, 0 and +1, 3 orbitals will be there. Now suppose you want to fill 5 electrons in this one, so you cannot fill it like 1 2 3, okay, 1 2 3 4 and 5. One second, I'll take one eraser. Yeah, suppose you want to fill 4 electrons here, okay, you want to fill 4 electrons here, and remember one rule that in each orbital, okay, in each orbital you can have only 2 electrons, okay, in each orbital, okay, how many electrons you can fill? Only 2 electrons you can fill. So now if you see we have 4 electrons to be filled, I can fill like this 1 2 3 and 4. What is this plus, like up arrow and down arrow represents plus half and minus half, okay. So if in one orbital both the electrons cannot have plus half, okay, because then the Pauli's rule will be excluded or will be violated. So you can have in one orbital 2 electrons if you are putting there, spin quantum number should be different, okay. So now this way we can fill, but that is wrong according to Hund's rule. Now what does Hund's rule say? Hund's rule says that all the orbitals should be first occupied one time, and after that the pairing should take place. Now for example, if I want to fill 4 electrons, I should fill first 1 electron to all the orbitals, then the 4th electron will pair here. Clear? So that is your Hund's rule of maximum multiplicity. Okay, now coming to the electronic configuration. So based on these all rules, we will try to write the electronic configurations of 2-3 atoms so that we can know the process, okay. So let us suppose write for nitrogen. Nitrogen atomic number is 7, right? And if you remember, what is the order of filling electrons? 1s, 2s, 2p, 3s, then 3p, then I have 4s, then I have 3d. Okay, I'm just doing examples with these 3, then you can continue the same thing. Now 7, and what is the thing that you should remember? Always remember that s orbital can hold 2 electrons, p orbital can hold 6 electrons, and d orbital can hold 10 electrons. Okay, so that we will do in a diagrammatic way and understand it very clearly. Okay, so now first is 1s. So 1s will have one box. Okay, I'll give 2 electrons here. So out of 7, 2 electrons are gone. Next we have 2s. Okay, so here I'll give 2 electrons. After 2s we have 2p, right? So now if you see in 2p I have 3 orbitals. Okay, now why I told 6 electrons? Because each orbital can hold 2 electrons. So 3 orbitals can hold 6 electrons, right? So now if you see here, out of 7 already 4 electrons are filled. We need to fill 3 more electrons. So according to the last rule, okay, these 3 electrons, each should get 1 electrons. Okay, then what is the configuration here? I can write 1s2, 2s2 and 2p3. Okay, next for example let us write for magnesium. Okay, so magnesium atomic number is 12. Okay, so if you write here, first we have 1s. Okay, so 1s I'll give 2 electrons here. Next I have 2s and it will have 2 electrons here. Next I have 2p and this will have 6 electrons, 1 2 3 4 5 and 6. So how many electrons have been done? 6 7 8 9 10. Okay, so 2 more electrons are left. So after 2p we have 3s. So here we have 3s and I'll get 2 more electrons here. So what will be the configuration here? It will be 1s2, 2s2, 2p6 and 3s2. Okay, now let us see one more example of, for example, iron. Iron is having atomic number 26. Okay, now if you see 26 I want to do, so first I'll do 1s. Okay, so we have 1s 2 electrons. Next I have 2s. 2s will have 2 electrons. Next I have 2p. Okay, so 2p will have 6 electrons. Okay, next I have 3s. 3s will have 2 electrons. Okay, next I have 3p. So 3p is having again 6 electrons. Okay, next I have 4s, and 4s is having 2 electrons. Okay, now after 3p, why did I fill 4s? You can see the order here. After 3p, 4s comes. Now till now, how many electrons we are already done? So 1, 2, 3, 4, and here 6. So 10, 11, 12, another 6, right? So 18 and here 20. So we are done with 20 electrons. We are left with 6 more electrons. So I have next is 3d, and in 3d I have 5 orbitals, and I need to fit 6 electrons. So 1, 2, 3, 4, 5 and 6. Okay, so what will be the configuration here? 1s2, 2s2, 2p6, 3s2, okay, 2p6, 3s2, 3p6, 4s2 and 3d6. Okay, so this will be the configuration. Okay, fine. So this is how you can solve this. Now let us do this question. Okay, so this question I have given you as a homework. I hope all of you would have solved this question. So the question is, what will be the longest wavelength in the Balmer series of hydrogen spectrum? So if you see the formula I told you, you need to calculate 1 by lambda is equal to 109677 by 1 by 2 square minus 1 by 3 square, right? So that means we need here 109677 into 3 3s are 9, here it is 4, and into 4 into 9, right? So if I solve this, it will be 109677 into I'll get 5 by 9 4s are 36. Okay, so that is in terms of centimeter inverse. So if I want to calculate now lambda, that will be 36 by 5 into 109677 centimeter. Okay, now whatever answer we'll give here, so let us do this calculation. So now if you solve this, we'll be getting like 0.00006567 centimeter. Okay, so now if I want to write it in terms of meter, right? So 1, 2, 3, 4 and 5. So I'll get okay, so you can see the units may be here some error, but you can see 6557. So correct answer here will be option number A. Okay, just check this calculation, and but you will be getting answer number A here. Okay, yes, once again 1, 2, 3, 4, 5, 6, 7, 8. Okay, so I'll get 6557 into 10 to the power of minus 8, right? I got this much. Okay, next we need to convert this centimeter to meter. That means again I need to divide by 100, right? So that will give me 6557 into 10 to the power of minus 10. This is in centimeter and this is in meter. Okay, so option number A. Okay, let us do next question. If a wavelength of photon is 2.2 into 10 to the power of minus 11 meter and h value is this much, then the momentum of the photon is. So photon is a particle, we consider it, so we can calculate its momentum. So here you need to use de Broglie formula, that is h by p, and p can be calculated by h by lambda. So h value is 6.6 into 10 to the power of minus 34 and wavelength value is 2.2, right? 2.2 into 10 to the power of minus 11. So this is 3 into 10 to the power of minus 4 minus 1, 3 minus 23. That is option number C here. Okay. Next question number, the number of angular and radial nodes in 3p orbital respectively are. So if you see, we have the formula of radial nodes as radial nodes is equal to n minus L minus 1, right? So for 3p, so we need n is equal to 3, L value, p value, right? So p value means SPD. So if you remember, SPD 0, 1, 2. So 3 minus 1, so that is 1. Okay, so I got 1 as the radial node. Okay, so that means the last option should be 1, so we can eliminate this option. Next, angular nodes, if you want to calculate, the angular nodes formula is nothing but direct L, simple L. What is the value of L here? Again L value is 1, that means it is 1 and 1, option number B. Okay. Next, question number 3. This question was asked in 2019. Two particles A and B are in motion. If the wavelength associated with A is 33.33 nanometer, the wavelength associated with B, whose momentum is 1/3 of A, is. Okay. So let us see here. We need to calculate the wavelength associated with B. Okay. So I can write that lambda A is equal to h by momentum of A. Okay. And lambda B is equal to h by momentum of B. Okay. So now let me take a ratio of lambda B by lambda A. Okay. So if I take lambda B by lambda A, then I'll get h by momentum of B into h by momentum of A. Okay. H can be cancelled because it is Planck's constant. So I'll get PA by PB. Okay. Now what is the relation between PA and PB? You can see that B momentum is 1/3 of A. That means PB is equal to 1/3 of PA. Okay, that I can substitute here. So lambda B by, what is lambda A value? 33.33. Okay, and PA and PB is 1/3 of PA. Okay, that means this can be written as 3 PA. Right, this one can be multiplied this side, so sorry, this one can be written as 3 and this multiplies, so 99.99 nanometer. Okay, we'll get. The option is again in the terms of meter, right? So I can write it as 99.99 into 10 to the power of minus 10 meter. Okay, now if I go this side, okay, then I can write it as 9.99 into 10 to the power of minus 9 meter. Okay, 1 second, 9.99 into 10 to the power of 1 second, 10 to the minus 10 meter. Okay, then if I make it like this, I'll get 99.33.33, right? So I'll get 99.99 into 10 to the power of minus 9 meter. So is there option like this? Okay, 9.99 we can write it as 10, right? 10 into 10 to the power of minus 9 meter. So that means it is 1 into 10 to the power of minus 8 meter. So 10 minus 8 is there. So option number A here. Okay. Next, question number 4. The orbital nearest to the nucleus is. So here this is also very simple question. So you should know that as the n, if the n value is less, okay, it is closer to nucleus. Okay, first we'll see the n value, then how to check L value. According to L value, S, P, D and F. S is closer, then P, then D, then F. So out of these all, this n values are less, 4s and 4f, and out of 4s and 4f, 4s will be more closer. Okay. Next, the correct set of quantum numbers for the unpaired electron of chlorine atom is. Okay, so you see here, what are the rule? N value can be anything from 1 to infinity. Okay, L value can be 0 to n minus 1. ML values can be minus L to plus L. Okay, so now if you see here, you need to find the correct set, right? Okay, so if I see that 2 is here, 0 is here, and 0 is here, and plus half is here. Okay, that seems, 1 second, sorry. Yeah, so this option seems to be correct. Next, if you see, we have here 3, 0, 0, plus minus half, right? So you cannot give plus minus half to, 1 second, the correct set of quantum numbers for the unpaired electron of chlorine atom. Okay, so first we need to write the electronic configuration, then only we can do it. So chlorine is having 17 electrons, right? So now if you write the electronic configuration, 1s2, 2s2, 2p6, 3s2. So how much we have done? 6, 7, 8, 9, 10, 11, 12 and 3p5. So if I draw like this, 3p, so we have like this 1, 2, 3, sorry, 3p, na? It has 3 orbitals, not 5. So 3p5 if I draw here. Okay, so 1, 2, 3, 4 and 5. So we need to tell the configuration of this particular unpaired electron. So here n value is 3, right? So we can eliminate these two options. So n value is 3. Then it is 3p, right? 3p. P value means L value should be 1. Here it is given 0, so eliminate this option. This is the correct answer, that is option number D. Okay. Next, question number 7. Consider the following sets of quantum numbers. Which of the following setting is not permissible arrangement of electrons? Okay, which is not permissible, you need to think. Okay, so if n value is L, then if n value is 4, then L value can be 0, that is correct. ML value can be 0, that is also correct. This can be minus half, that is correct. Okay, next if you see, if n value is 5, then L values can be 0, 1, 2, 3, 4, right? So that means 3 is also possible and 0 is also possible and plus half is also possible. Next if you see here, if n value is 3, L values are 0, 1, 2 and ML values will be minus 2 to plus 2, so that is also correct, this is also correct. Next if you see here, n value is 3, so L value can be 0, 1, 2, that is correct. ML values will be from minus 2 to plus 2, right? It cannot be minus 3. So this set is wrong, that is why here the answer will be option number D. Okay. Next, this question is a homework question. Okay, try this question and we'll answer this in the next class. Okay, so students, this was the end of the structure of atom chapter. Tomorrow's class we will be doing the previous year questions of structure of atom. Okay, so now this chapter is very lengthy, but what we'll do is we'll analyze the previous year questions and we will pick out the most important topics. Okay, so tomorrow I'll be doing the previous year questions from this particular chapter. So if you want to prepare, stay tuned for tomorrow's class. Okay, and if you are finding these lectures helpful in your preparation, do not forget to subscribe the channel.